Hi everybody, welcome back to my channel on Feynman integration. Today we're going to be evaluating an integral very similar to the one I did last time. This was the one I did last time and it was equal to 2 pi squared. We're going to change the integral slightly by changing that x minus 1 to an x plus 1. And oddly enough, that's going to have the effect of changing the answer to a constant multiple of pi cubed instead of a constant multiple of pi squared. And also we're going to be using this result, that is the alternating sum of the reciprocals of the odd cubes, which evaluates to pi cubed over 32. And maybe at some point on this channel I might show how that's derived. It involves Fourier analysis, and I really haven't gone over that at all on this channel. But I'm going to kind of cheat a little bit and just use that result. That is true. You guys can look up that result for yourselves if you want a good explanation of why it's true. Like I said, I might show it at some point on this channel. But anyway, yeah, that integral evaluates to pi cubed over 2. And here's how you get there. First step is we will break up this integral into two separate integrals, one going from 0 to 1 and the other going from 1 to infinity. So I is going to be equal to the integral from 0 to 1 of the natural log squared of x over square root of x times x plus 1 squared dx plus the integral from plus the integral from 1 to infinity of natural log squared x over square root of x times x plus 1 squared dx. And then on this integral right here, we will make the substitution that x is equal to 1 over u, and therefore dx is equal to negative 1 over u squared du. Let me write that better. Let me write it so it all fits. So we're saying that x is equal to 1 over u. Therefore, dx is equal to negative 1 over u squared du. All right. So what would that give us for this integral right here? Well, we'd have the integral from 1 over 1, which is 1, to 1 over infinity, which is 0. Natural log squared of x would become natural log squared of 1 over u. Natural log 1 over u is simply negative natural log u. Squaring that would just give us natural log squared u. So natural log squared u. And then the square root of 1 over x is 1 over the square root of x. So that would basically just bring this to the top as a square root of u. And then we'd have, in the denominator, we'd have 1 over u plus 1 all squared times negative 1 over u squared du. We'll use this negative to switch the bounds. We'll distribute this u squared inside the parentheses there. So this will just give us u plus 1. And this will be du. And then I'm just going to switch all these back to x's over here. So we have plus the integral from 0 to 1 of the square root of x natural log squared x over x plus 1 squared dx. All right. So now we are going to create a function of t that closely resembles both of these. So our function of t is going to equal the integral from 0 to 1 of x to the t, natural log squared x over x plus 1 squared dx. All right. And now we can see that f evaluated at negative 1/2 plus f evaluated at 1/2 will give us back our original integral. Because f at negative 1/2, that would recover this part right here. This x to the t would just become an x to the negative 1/2, which would be a 1 over the square root of x. And f at 1/2 would give us the square root of x. Okay. So now what? You know what? I'm sorry, I made a mistake there. Our function of t does not include that natural log squared x there. That comes from taking two derivatives with respect to t of that equation. So I'm going to write that down. Our f double prime of t is equal to the integral from 0 to 1 of x to the t natural log squared x over x plus 1 squared dx. And this will become double prime and double prime. So yeah, f double prime at negative 1/2 plus f double prime at 1/2 will give us I. All right, so now all we have to do is evaluate this integral right here and then plug in these numbers to recover our original integral. But we can't really do that with this, so we need to find a new way to represent this. And we'll do that by finding a new way to represent our f of t. All right, so let's recall that the sum from n equals 0 to infinity of 1 over 1 minus x is equal, of x to the n, of x to the n is equal to 1 over 1 minus x on the integral negative 1, on the interval negative 1 to 1. One of those bounds is included, I forget which one. So if we put a plus here instead of a minus, that would become a negative x to the n, which is just negative 1 to the n times x to the n. Negative 1 to the n, x to the n. So that is still true. And now what we will do is we will take a derivative with respect to x on both sides of this equation right here. And what you'll get if you do that is that the sum from n equals 0 to infinity of negative 1 to the n times the derivative with respect to x of x to the n, which would just be n times x to the n minus 1, is equal to the derivative with respect to x of this thing. Well, this is 1 plus x to the negative 1. So taking a derivative of that, this would become a negative 2, and that would become a negative. So that is equal to negative 1 over x plus 1 squared. All right. All right, so that's true. So we can, well, let's bring that negative to this side. So now that's true. So now we can replace this 1 over x plus 1 squared with this. So let's rewrite our f of t. And we'll rewrite it up here. So our new f of t is going to be equal to, well, let's see. We'll bring out the negative sign right away. So it's going to be negative integral 0 to 1 of x to the t times the sum from n equals 0 to infinity of negative 1 to the n times n x to the n minus 1 dx. And we will use Fubini's theorem to switch the sum and integral signs here. So this will become the integral from 0 to 1. And this will become the sum from 0 to infinity. Negative sum from n equals 0 to infinity. All right, we'll bring this x to the t inside our integral. So this will become x to the n plus t minus 1. X to the n plus t minus 1. All right. And then we can bring the negative 1 to the n times n outside the integral. I'll do that. Negative 1 to the n times n. We'll just be left with x to the n plus t minus 1 dx. All right. Evaluating this integral, that would just give us 1 over n plus t. So we can get rid of this entire thing and make this 1 over n plus t, and we'll put this negative 1 to the n times n on the top there. Okay. All right, so now there's our expression for f of t. All right, now let's take two derivatives with respect to t of this function to get a new representation for f double prime of t. All right, well, what's two derivatives with respect to t of 1 over n plus t? Well, that's n plus t to the negative 1. Bringing down the negative sign, and then we increase this, and then we bring down a negative 2 to make it a positive 2, and we would increase this again. So that would simply become negative 2 times the sum from n equals 0 to infinity of negative 1 to the n times n over n plus t cubed. So this is f double prime of t. Okay, so now we can get our I by first evaluating this function of t at the point negative 1/2, and then adding it to f double prime at 1/2. So what is f double prime at negative 1/2? Well, we would have negative 2 times the sum from n equals 0 to infinity of negative 1 to the n times n over n minus 1/2 cubed plus negative 2, so minus 2 times the sum from n equals 0 to infinity of negative 1 to the n times n over n plus 1/2 cubed. Okay. So now what we're going to do is we will increase the index of this. We'll make this n going from 1 to infinity. But since we increased our n in the index here, we need to decrease it in the actual inside here. We add 1 to n here, subtract 1 from n here. So this is going to be n equals 1 to infinity. And this will become negative 1 to the n minus 1. And this will become n minus 1. And n minus 1 plus 1/2 is just going to be n minus 1/2. Okay. And then what we'll do is we will notice that we don't even need the 0th term of this sum, because the 0th term of this sum is simply going to be 0. So we can actually increase that to n equals 1 and not even do anything. We could have done that here as well. It's a choice. We can either add 1 and then subtract 1, or we can just simply add 1. It doesn't matter. And now what I'd like to do is let's match up this n term with this n term. And in order to do that, we would need to get rid of this negative 1 in front of the n. But that will just have the effect of changing it to plus 2. All right. So now what we'll notice is that we have negative 2 times this sum, and we also have a positive 2 times that sum. Because we can actually break up this sum, if we wanted to, into two separate sums using this n and this negative 1. And you'll notice that this negative 2 times this sum will cancel out with this positive 2 times the same sum. So, in other words, this whole thing right here can simply be written like, let's see, the n terms would cancel out, and we would be left with negative 2 times the sum from n equals 1 to infinity of, let's see, yeah, we're just still going to have negative 1 to the n. Am I doing this right? Am I forgetting a negative sign or something? The n terms would cancel out, and we'd be left with plus 2 times this negative 1. So yeah, that'd be a minus 2, and everything else would stay the same. All right, so that's negative 1 to the n over n minus 1/2 cubed. Okay, so we're getting close. Let's see. Now we want to make this kind of the same as this. So how are we going to do that? Well, let's see. We have a 2n minus 1 cubed, but an n minus 1/2. So, well, let's see. We could multiply the denominator here by 8, and then multiply the entire thing by 8. So this would become negative 16 times this. And we'd have 2n minus 1. All right, almost there. Let's see. The index matches. This part doesn't match. We have the negative 1 to the n plus 1. So we need to add a plus 1 there, but that would have the effect of just multiplying the entire thing by negative 1. So we can take care of that like that. So now we have 16 times this exact sum right here. Well, 16 times pi cubed over 32 is going to give us pi cubed over 2. And that is exactly what we sought out to show. So yeah, there you go. that's how you get the answer to that integral, using Feynman integration and the fact that this sum evaluates to pi cubed over 32. So it's really neat that simply by changing that from a -1 to a +1, I mean, I would expect it to have still been a multiple of pi squared, but for some reason, it makes it a multiple of pi cubed, which I find kind of interesting. So anyway, I hope you found that as interesting as I did, and see you next time.